Okay, hello everyone in a new video. So we have reached part 5 of chapter 6, which is the chapter of center of mass for grade 11 students. In this one we are going to solve some exercises. So exercise number 11, each of documents 1, 2 and 3 represent the forces F1, F2 and F3 in a space reference system IJ. Determine in terms of F1, F2, F3 and theta and alpha the projections of F1, F2 and F3 along the x-axis and the y-axis. So the projection is given by the components Fx and Fy. Then we need to write these forces in the vector notation. Let's start by document 1. So in this document we have 3 forces that are given by F1, F2 and F3. So now before we start projecting and determine the vector notation of each force, let's determine the angles. So the angle that the forces make with the axes. So notice that first of all this line is parallel to this line, okay? So notice that in this case, if this is the angle theta, so this is the angle theta, and the reason is given by alternate interior angles. And because this is theta and this is 90 degrees, so the sum of these two angles, this one plus this one, must add up to pi by 2. So this is simply pi by 2 minus theta. And as for this quadrant here, so notice that this line is parallel to this line, so if this is alpha, then this is alpha, and the reason is given by alternate interior angles. And this angle here is 90 degrees, so this angle plus this angle is pi by 2, so this is simply given pi by 2 minus alpha. Okay, so let's start by the force F1. So the force F1 has two components, the x component and the y component. So as for the x component, so notice that in this case F1 is completely parallel to the y-axis, so F1x is 0, and F1y, so notice that F1 is pointing in the negative direction of the y-axis. In this case, no need to project, simply this is given by minus F1. So in this case, the vector notation of F1, which is equal to F1x multiplied by the unit vector I plus F1y multiplied by the unit vector j is equal to 0i minus F1j, which is equal to minus F1j. So the F1 vector is equal to minus F1j. Now as for the force F2, so let's start by the x component of this force. Notice that this force is pointing in the same direction of the x-axis, so it's positive, multiplied by its magnitude, which is F2, times the cosine of the angle between F2 and the x-axis, and this is given by the angle theta, so this is F2 cosine theta. Now as F2y, so notice that F2 is pointing in the positive direction of the y-axis, so it's positive, multiplied by its magnitude, which is F2, multiplied by cosine of pi by 2 minus theta, and cosine of pi by 2 minus theta is equal to sine theta. So in this case, the vector notation of the force F2 is given by F2 cosine theta multiplied by the unit vector I plus F2 sine theta multiplied by the unit vector J. Now as for the force F3, so let's start by F3x. So notice that in this case F3 is pointing in the negative direction of the x-axis multiplied by the magnitude of F3 times the cosine of the angle between F3 and the x-axis, which is the angle alpha, so cosine alpha. Now F3y, notice that F3 is pointing in the positive direction of the y-axis, so plus F3 multiplied by cosine of the angle between F3 and the y-axis, which is pi by 2 minus alpha. So this is equal to F3 sine alpha. So in this case, the vector notation of F3 is equal to minus f3 cosine alpha multiplied by the unit vector I plus f3 sine alpha multiplied by the unit vector G. Then this is it for document 1. Now let's proceed to document 2. Now before we start projecting the forces, let's determine the angles. So we are interested in the angles between the forces and the axes. So notice that this line is completely parallel to this line. So if this is alpha, then this is alpha, and the reason is given by alternate interior angles. Okay, and in this case this is given by pi by 2 minus alpha. If this is theta, then this is theta, and the reason is given by alternate interior angles, and this is given by pi by 2 minus theta. So we are supposing that this line is completely parallel to this line. Now let's start by document 2. Then we will start with the force F1. So the x component of F1, so notice that F1 is completely parallel to the y-axis, so F1x is 0. And as for F1y, it's pointing in the negative direction, so it's minus F1. No need to project because it's completely lying on the axis. Then in this case, the vector notation of F1, which is given by F1x I plus F1j F1yj is equal to 0i minus F1j, which is equal to minus F1j. So the F1 vector is equal to minus F1j. Now as for the force F2, so notice that here in the F2, as for the x component, it's pointing in the positive direction, so plus F2 multiplied by the cosine of the angle, which is pi by 2 minus alpha. So this is equal to F2 sine alpha. Now as for F2y, so notice that F2 is pointing in the positive direction of the y-axis, so it's positive F2 multiplied by cosine alpha, in which alpha represents the angle between F2 and the axis that we are projecting on, which is the y-axis. So in this case, the vector notation of F2, which is given by F2x I plus F2yj is equal to F2 sine alpha multiplied by the unit vector I plus F2 cosine alpha multiplied by the unit vector G. Now as for the force F3, so F3x, notice that F3 is pointing in the negative direction of the x-axis, so it's minus F3 times cosine of the angle between F3 and the x-axis, and this is given by pi by 2 minus theta. So this is equal to minus F3 sine theta. As for the y component, notice that F3 is pointing in the positive direction of the y-axis, and the angle in this case is given by theta, so it's given by cosine theta. Then in this case, the vector notation F3, which is equal to F3x multiplied by the unit vector I plus F3y multiplied by the unit vector j, which is equal to minus F3 sine theta multiplied by the unit vector I plus F3 cosine theta multiplied by the unit vector g. So in documents 1 and 2, so what do they represent in physical situations? So they may represent a box, and here we have, say for example, a box attached here to a strings, and F2 and F3 they may represent the tensions T2 and T3, in which F1 may represent the weight W. Okay. Similarly for document 2, but the definitions of the angle in each document are different. Now as for document 3, so before we start solving for the projections, let's analyze the angles. So if this is alpha and the angle between the x-axis and the y-axis is 90 degrees, then this is pi by 2 minus alpha. Okay, now notice that here we have the angle theta, which represents the angle of inclination. If this is theta, so notice that this line is completely vertical, so it's vertical, so it's parallel to this line, so this angle is 90 degrees or pi by 2. So this angle is pi by 2 minus theta, because the sum of angles in any triangle must be 90 degrees, 180 degrees. So and notice now that in this case this line is parallel to this line, so if this angle is pi by 2 minus theta, then this angle also is pi by 2 minus theta, and the reason is given by corresponding angles for two parallel lines. Okay, so simply this angle here is pi by 2 minus theta, and this angle here is theta, because notice that this angle and this angle must add up to 90 degrees. Now we are ready to project the forces. Let's start by the force F1. So F1 acts, notice that F1 is pointing in the negative direction of the x-axis, so it's minus multiplied by its magnitude times cosine of the angle between the force and the x-axis, which is pi by 2 minus theta. So this is equal to minus F1 sine theta. As for F1y, which is equal to, notice that F1 is pointing in the negative direction of the y-axis, so it's minus F1 multiplied by the cosine of the angle between the y-axis and F1, which is theta. Now for the vector notation, F1 is given by F1xi plus F1yj, which is equal to minus F1 sine theta I minus F1 cosine theta j. As for the force F2, then F2x, notice that in this case F2 is completely parallel to the x-axis and in the positive direction, so this is plus F2, and F2y is 0. So the vector notation of the force F2, which is given by F2x plus F2yj, is equal to F2i plus 0j, which is equal to F2i. So this is the force vector F2. Now as for the force vector F3, now F3x, so notice that F3 is pointing in the positive direction of the x-axis, so it's plus F3 multiplied by the cosine between F3 and the x-axis, which is pi by 2 minus alpha, which is equal to F3 sine alpha. And as for F3y, notice that F3 is pointing in the positive direction of the y-axis, so it's plus F3 multiplied by the cosine of the angle between F3 and the y-axis, which is alpha, so cosine alpha. Now in this case the force F3, which is equal to F3x I plus F3yj, so this is equal to F3 sine alpha I plus F3 cosine alpha j. So F3 is simply given by F3 sine alpha I plus F3 cosine alpha j. And now let's move to the next exercise, which is the final exercise, exercise number 12. So let's, okay, similarly each of documents 1, 2 and 3 represent the forces F1, F2 and F3 in a space reference system OIJ. Determine in terms of F1, F2, F3, theta and alpha the projections of F1, F2 and F3 along the x-axis and the y-axis. Then write these vectors and write these forces in the vector notation. Let's start by document 1. And before we project, let's indicate the angles that the forces make with the x and the y-axis. So notice that if this is alpha and this is pi by 2, then this is pi by 2 minus alpha. So if this is pi by 2 minus alpha, then this is simply alpha. Why? Because notice that if we prolongate this line, then if we label these points, then this is the point A, B. Let me make it clear. So if this is alpha, then this is pi by 2 minus alpha. Suppose that this is the point A, this is the point B, and if we prolongate this line, then this is the point C. So notice that ABC represents a right triangle. So this is A, B, and C. This is a right triangle at C. So this is pi by 2, this is pi by 2 minus alpha, and this is alpha. Okay, why? Because the sum of these angles must be 180 degrees, which is pi. So if you check that pi by 2 minus alpha plus pi by 2, so this cancels out to give us pi, which is 180 degrees. So whenever we have 90 degrees in a triangle and one of the angles is alpha, then the other is pi by 2 minus alpha. So if one of the angles is pi over 2 minus alpha, then the other is alpha. And notice that if this is alpha and this line is parallel to this line, so this is also equal to alpha, and the reason is given by corresponding angles for two parallel lines. So now if this is pi by 2 minus alpha, so this angle is simply what? Alpha. And this is pi by 2 minus alpha. So if this is theta, then this is simply pi by 2 minus theta. Okay, so now let's start projecting. Let's start by the force F1. So F1x, notice that here in this case, F1 is pointing in the negative direction of the x-axis, so it's minus F1 multiplied the cosine of the angle between the x-axis and F1, which is alpha, so cosine alpha. F1y, which is equal to F1y. So notice that F1 is pointing in the negative direction of the y-axis, so it's minus F1 times cosine of the angle between the force F1 and the y-axis, which is pi by 2 minus alpha. So this is equal to minus F1 sine alpha. Then the force F1 in the vector notation is given by F1xi. Then this is equal to minus F1 cosine alpha I minus F1 sine alpha j. Now as for the force F2, so notice that F2 is pointing in the positive direction of the x-axis, so it's plus F2 multiplied by the cosine of the angle between F2 and the x-axis, which is theta. Now as for F2y, notice that F2y is pointing in the positive direction of the y-axis, so it's plus F2 multiplied by the cosine of the angle between F2 and the y-axis, which is pi by 2 minus theta. So this is equal to F2 sine theta. And because the force F2 can be written as F2x I plus F2yj, so this is equal to F2 cosine theta multiplied by the unit vector I plus F2 sine theta multiplied by the unit vector j. Now as for the force vector F3, Notice that f3 in this case is completely parallel to the y-axis, so simply f3x is equal to 0, no projection, and f3y is equal to plus f3, so f3 vector is equal to f3xi plus f3yj, which is equal to 0i plus f3j, which is equal to f3j. So this is it for document 1. Now for document 2, then before we start analyzing the document, let's determine the different angles. So notice that here, if this is theta, if we prolongate this line, so the triangle consisting of the points A, B, and C, ABC is the right triangle at A, so this is 90 degrees, so this is pi by 2 minus theta. So this angle here is pi by 2 minus theta. And notice that this line is parallel to this line. If this is pi by 2 minus theta, then this angle here is also pi by 2 minus theta, and the reason is given by corresponding angles for two parallel lines. So this angle here is pi by 2 minus theta. And if this angle is pi by 2 minus theta, this is theta because they must add up to pi by 2. Okay, so and the other forces are completely parallel, so let's start by the force F1. Then F1x is equal to, it's pointing in the positive direction of the x-axis, so it's plus F1 multiplied by cosine pi by 2 minus theta, which is equal to F1 sine theta. So F1x is given by F1 sine theta. Now F1y is equal to, notice that F1 is pointing in the negative direction of the y-axis, so it's minus F1 multiplied by the cosine between the force F1 and the y-axis, which is given by theta. So this is minus F1 cosine theta. In this case, the vector notation of F1 is given by F1 xi plus F1 yj, which is equal to F1 sine theta multiplied by the unit vector I minus F1 cosine theta j. Now as for the force F2, so notice that F2 is completely parallel to the y-axis, so F2x is equal to 0 and F2y in the positive direction is plus F2. So in this case, the vector notation of F2, which is equal to F2xi plus F2yj, is equal to 0i plus F2j, which is equal to F2j. Now as for the force F3, then F3x, notice that F3 is completely parallel to the x-axis in the negative direction, so it's minus F3. And F3y is equal to 0. Then in the vector notation F3, this is equal to F3xi plus F3yj, which is equal to minus F3i plus 0j, which is equal to minus F3i. And now as for the final document, so if this angle is alpha, then this is pi by 2 minus alpha. And the reason is given that the sum of angles in any triangle must be pi over 2, pi, which is 180 degrees, so this will cancel this, and pi by 2 plus pi by 2 is 1 pi, which is 180. Now this is pi by 2, and we complete this triangle. We complete the prolongation of F1, so this is A, B, C, so it's a right triangle at A, which means that this is pi by 2 minus alpha, then this is alpha because they must add up to pi, and this line is parallel to this line, so this is also is equal to alpha. So in this case, this angle is given by alpha, and if this is alpha, then this is pi by 2 minus alpha. Let me make some space. So we are in document number 3. So as for the force F1, its x component, notice that F1 is pointing in the positive direction of the x-axis and the angle is alpha, so plus F1 cosine alpha. F1y, notice that it's pointing in the negative direction of the y-axis and the cosine of the angle, and the angle is pi by 2 minus alpha. So this is equal to minus F1 sine alpha. Then in the vector notation, F1 is equal to F1xi plus F1yj, which is equal to F1 cosine alpha I minus F1 sine alpha j. Now as for the force F2, so notice that F2 is completely parallel to the y-axis, so F2x is equal to 0 and F2y is equal to plus F2. And in the vector notation, F2, which is equal to F2xi plus F2yj, which is equal to 0i plus F2j, which is equal to F2j. Now as for the force vector F3, so F3x pointing in the negative direction and the angle is theta, so minus F3 cosine theta. As for the y, so notice that if this is theta, then this is pi by 2 minus theta, so plus pointing in the positive direction F3 cosine of pi by 2 minus theta, which is equal to F3 sine theta. So in this case, in the vector notation, F3, which is equal to F3x I plus F3yj, which is equal to minus F3 cosine theta multiplied by the unit vector I plus F3 sine theta multiplied by the unit vector j. So this is F3. Then that's it for me in this video, guys. See you soon in a new one.